So, hi everyone, this is Tolga, and I will present our joint work with my friend Umut on synchronizing multi-view matches. So, given a shape collection or image collection, many computer vision applications begin by establishing pairwise matches. And correspondences computed in this way are subject to noise and inconsistency when multiple of those are matched together. Exploiting the loop closures in such multi-view scenario, our goal is then to correct or improve these matches such that the resulting correspondences are cycle consistent. Moreover, we would like to provide uncertainty or confidence information for the solutions we compute. While this problem can be solved with many previous methods, none of those can yield an estimate of an uncertainty. So the main idea is we assume that the pairwise correspondences can be encoded into total permutation matrices. In this work, we do not address the case of partiality. Given Pij, the observed relative permutations, we minimize what is called the cycle consistency loss over the entire hypergraph to compute the absolute permutations that reorder the points to a canonical configuration, ensuring global agreement. So as the minimization is done in the permutation space, we have a discrete optimization problem. This is hard to tackle. So like many, we relax the problem in the parameter space to the convex hull of permutations, the Birkhoff Polytope, and contribute as follows. We are for the first time using Riemannian optimization techniques on the relaxed parameter space, this Birkhoff Polytope, and we are also the first to provide reliable confidence estimates for this problem. So now I would like to take a look at the geometry of the parameters, so I will make explicit use of this. Binary permutation matrices constitute discrete vertices of a convex simplex. So, and this denotes the set of matrices whose elements sum to a fixed number. Permutations also belong to what is called the orthogonal group. And the Birkhoff polytope, encapsulated within the simplex and the orthogonal group, is the convex hull of permutation matrices. It's the manifold of double stochastic matrices whose row and column sums equate to 1. These objects share the common center of mass. We will also speak of the tangent space of the Birkhoff polytope in the context of Riemannian geometry. It is only recently that Doig et al. Endowed the Birkhoff polytope with a Riemannian structure, and we will use these operators to tackle the optimization problems that we have. So, here's how we solve the aforementioned tasks. We first relax the parameters to live on the Birkhoff polytope, matrices whose row sums and column sums are 1. We then solve the same optimization problem, but this time on the new manifold. So thanks to the Riemannian methods, we can now omit all the projected algorithms and use unconstrained minimization schemes such as Riemannian limited memory L-BFGS. So next, we characterize the full posterior distribution by drawing samples on it and use these samples in uncertainty or confidence estimation. To draw samples on the Birkhoff polytope using MCMC methods, for instance, we propose a new algorithm, and that is called Birkhoff-Riemannian Langevin Monte Carlo. So here is how this would work. Consider the typical Riemannian gradient descent, in which we first compute the Euclidean gradient and project it onto the tangent space of the current iterate to get the Riemannian gradient. And we use this vector to retract the current point to obtain the iterate in the next time step. And we show that using Langevin stochastic dynamics, this algorithm can simply be converted to a sampler by adding a Brownian motion term on the Euclidean gradient. This is a first-order scheme, which we will call retraction Euler integrator. So, our minimization scheme yields high-quality outputs that outperform the state-of-the-art in general. In this example, the red lines denote wrong matches and the blue the correct ones. It is visually apparent that we can improve upon the initial guess that is computed by, for instance, a simple Hungarian matching. Right. And we finally show uncertainty estimates here. For clarity, we pick examples where our solution is not particularly good. We show in column C the estimated correspondence matrix, which would ideally be identity. And note that if we instead allow top 2 confident matches to survive, so for instance in column E, the resulting match matrix becomes diagonally dominant, showing that we can correct confusions by the samples we draw. The rightmost column shows the corrected matches with confidences colorized. So I will pause for a moment here for you to look. Okay, thank you. And I can see you maybe at poster 159.